Good morning, everybody. So the topic of today's lecture is something called a stack. And so there's one of the things that every computing science student learns, regardless of where you learn your computing science. You will eventually take a course called data structures. So a stack is an example of a data structure. A data structure is simply, I guess, if you think of it in terms of software, it's a piece of software that organizes information in a useful and hopefully efficient way. And so a stack is probably the simplest data structure that you would learn about in computing science. And so this slide here shows you some examples of real-world stacks of stuff. We've got a stack of files, we've got a stack of books, we've got a stack of pancakes. So in computing science, the stack data structure would be the software analog of these things here. All right, so common to all of these piles of stuff is that there's this notion of the top of the stack, right? So here this arrow is pointing to the top book of a stack. And so classically, a stack data structure only lets you manipulate the data structure at the top of the stack. So there's only two operations. Right? So if you can only do something with the book on the top of the stack, there's only two things you can do. You can either take it off the stack, right, which reveals a new top of the stack, or you can put a book on top of the current top of the stack, right, which moves that arrow up one. Right? And so the stack data structure classically only supports those two operations. Right? So there's an operation called push, which is adding something to the top of the stack. And there's an operation called pop, which removes the thing on top of the stack. In Java, if you try to pop an empty stack, you would probably throw an exception. Right? In Python, you'd probably raise an error of some kind. Right? So trying to remove something from the top of an empty stack is generally considered to be an error. Right? Okay, so a picture of what happens when you, so I'm going to illustrate the two operations using some pictures here. So I'm going to start with an empty stack, and I'm going to make a stack of strings in this case. So if we start with an empty stack and you push a string on top of the stack, right? So st is my stack, right? Push is my method, and this is a stack of strings, so I'm going to push a string on top of the stack. Right? You can see here that you now have a stack of size 1, right? And the top element of the stack is this string a, right? And so that arrow top is always going to point at the top element of the stack. If you push a b onto the top of the stack, well, the string b gets added to the top of the stack, right? And the top of the stack moves up by 1. Right? And then pushing a c, and then a d, and then an e results in a stack of 5 elements. Okay, so what happens when you pop an element from the top of the stack? So if I pop an element from the top of the stack, whatever was on the top of the stack gets returned to the caller. Right? So in this case, s is going to be the string e, because e was the previous element that was on the top of the stack. Right? So you remove that element from the top of the stack, and you're left with a stack of size 4. Right? If you pop the d gets returned back to the caller, so s now refers to the string d, right? And the top of the stack goes down by 1. Right? And so on, and so on, and so on. Right? So when you pop all the elements off the stack, you're now in the situation where you have an empty stack again. Okay, so this data structure doesn't look particularly useful at first glance. However, they turn out to be enormously useful. They are one of the fundamental data structures in computing science. Right? So they are widely used in computer science, programming, and in computer engineering. If you've ever used a piece of software that has undo and or redo functionality, so PowerPoint, Word, pretty much any editor these days. The undo and redo parts of the program, they're probably implemented using a pair of stacks. They're widely used in parsing problems. So problems where you're trying to get the computer to read something, right? So read a language, for example. It turns out that stacks are very useful in those types of problems. I'm going to show you in a little bit how recursive methods are typically, how you can turn a recursive method into a non-recursive method using a stack. Right, well, that's the bottom one there. Right? And this is, the reason this works is because that in many programming languages, there actually is a stack that stores information about what method or function is currently running. Okay, so I guess a first example of a use of a stack, it's a bit silly and it's a bit inefficient, but if you have a list or a sequence of some kind and you would like to reverse the sequence, then one way to do it is to use a stack. Right? The reason this works is because it exploits the way that the stack functions. Right. Okay, so I'd like to reverse a list. Now, previously in the course, we saw how to reverse an array. You can use the exact same technique to reverse a list. Right? You swap the first and last elements of the list, then you swap the second and second last, and so on and so on and so forth. Right? An alternative way is the following. So I'm going to reverse this list T. T. And instead of reversing the list, I'm going to return a new list containing the elements of T in reverse order. All right, so first of all, I'm going to make a new list to hold the reversed list. Right? I'm going to try to leave T intact, so I'm not going to change T. Right? I'm going to make a stack. And then all I'm going to do is I'm going to iterate over the original list. Right? So for each string S in the original list, right, I'm going to take that element in the list and push it on top of the stack. Right? So basically all I'm doing is I'm copying the elements from T and putting them onto the stack. Right? Now I'm going to take the elements out of the stack until the stack is empty. Right? So while the stack is not empty, I'm going to pop the stack, right? And I'm going to take whatever element gets popped off the stack and add it to the result. Right? And I claim that after doing this, the result is contains the elements of T in reverse order. Right? And if you draw a little picture of this, or if you can visualize it in your head, it should be obvious why this works. Right? So there's your list, original list T. Right? We're going to make an empty stack, so there's my empty stack. I'm going to iterate over the list T, so ABC. And as I iterate over the list, I'm going to push these elements onto the top of the stack. Right? So I'm going to push the A on top of our empty stack. Right? Then I'm going to push the B on top of our empty stack, and I'm going to push our C on top of the empty stack. Right? So notice that when the first element in the stack is at the bottom of the stack. Sorry, the first element in our list is the bottom element of the stack, and the last element in our list is the top element of the stack. Right? So when I start to pop the elements off the stack, it's the C that's going to come out first. Right? The last element in is the first element out. Right? So as I pop the stack and add them to the result, right, the result is simply the original list T in reverse order. Right? Okay, so I call this an inefficient way to reverse the list, right, because you need to create this extra data structure here. Right, so here we're creating a list, we're creating a stack, which, at this point here, right, if you have n elements in the list, you now have n elements in the stack as well. Right? So we require on extra storage to reverse the list. Right? Okay, so a stack looks a lot like a list. Right? If you look at this picture, if I go back to this picture here, right? So if you sort of turn your head sideways, right, that ABC looks a lot like the ABC that's sitting here. So pushing an element onto the top of the stack, right, you can imagine that's like adding an element to the end of a list. Right? And if you pop an element from the top of the stack, that looks a lot like removing the last element in a list, right, or removing the element from the end of the list. And so what does that mean? It means, well, you can probably implement this thing using a list. Right? And you can. Right? So here's our class stack. This is going to be a stack of strings. Right? So if you implement this using a list, you're going to have a field. Right? That's a list of some kind, so it's going to be a list of string. Right? Here I've chosen to use array list. Right? To implement the constructor, right, you have to recall, what does every constructor do? Well, it has to initialize the fields of your class, so we need to make a new array. Right? So our constructor simply makes a new empty array list. I told you that at the beginning of the lecture, classically stacks only support 2 operations. Typically, you would add more. So for example, it's probably useful to know how many elements are in the stack. Right? So that we're going to call that size. right? If you want to know how many elements are in this particular stack, you just need to know how many elements are in the list. So you can just return the size of the list. Right? Pushing an element onto the stack is like adding an element to the back of that list. Right? And that's exactly what the add method does, right? It adds an element to the end of a list. Right? And removing an element from the, popping an element off the stack is like removing an element from the end of the list. Right? The element at the end of the list has index size -1, so I can just call remove, passing in that index, and that removes the element from the end of the list. Right? The remove method for a list also returns the element, which is good because I need to return the element back to the caller when we pop the stack, so I'm just going to return elem here. Right? And so I haven't told you this yet, but in an array list, when you remove something from the end of the list, right, that always runs in constant time. So that runs in O1 time. Adding an element to the back of the list, of an array-based list, usually runs in constant time as well. Every once in a while, though, adding something to the end of a list requires O(n) time. Right? So in an array-based list, the way this thing works is that it uses an array to hold the elements of the list. Right? And so when you make a new array list, what happens is that you end up creating, so the constructor will create a new array, but the array will have some finite length, right? So it won't be an array of length 0, it'll probably be an array of length of some small length. So say 8 or 16, right? And so that list can hold 8 or 16 elements until the array becomes full, right? If you keep on adding stuff to the list, eventually the array becomes full, and then when you add something else, what happens is the list class makes a new array, copies the elements from the old array into the new array, and then, so the new array is larger than the old array. And so now you can add extra elements to the array-based list. Right? So every time the array-based list has to resize itself, it resizes its internal array. That operation takes O(n) time, where n is the number of elements in the array. Right? So this is usually in O1, but every once in a while it requires O(n) time. So push in this case has worst case complexity big O of n. All right, so I mean that looks pretty easy to do, right? I think most of you should be able to confidently implement a stack using a list. Right? But there are other ways to do this. There's at least 2 other ways to do this. Right? So instead of using a list, you could use an array to store the elements. Right? Now the disadvantages of using an array is that there's no handy add method or remove method in an array. Right? And so you're going to have to manage the array yourself, which is what we're going to do shortly. Right? You could also use a linked structure. So I'm not going to describe that in any detail right now. It's probably going to be the next lecture, so on Friday, where we implement the stack using a linked structure instead. Right? So there are advantages and disadvantages to implementing a stack in the 3 different ways. And so we just learned about interfaces. And so we can consider creating an interface for all stacks. Right? And then we can consider implementing our stacks in the 3 different ways. Right? So write 3 different classes. Well, here's one already. Right? We can write an additional 2 classes, right, that implement a stack, one that uses an array, one that uses a linked-like structure. Right? And then we can analyze what are the advantages and disadvantages of the 3 different stacks. Right? If there are any significant advantages or disadvantages, right, then we can provide anybody who wants to use our stack classes with the different implementations. We can tell them what are the advantages and disadvantages of each, and they can pick the one that's most appropriate for their purposes. And that's exactly what the Java standard library does, right? So it provides you with multiple list implementations, it provides you with multiple set implementations, and multiple map implementations. Right? And you pick the user picks the one that's most appropriate for the problem they're trying to solve. Right. All right, so that wraps up the previous set of lecture slides. So the next set of lecture slides is Deck 21, and that's the set of slides called stacks. All right, so before we look at the implementation of an array-based stack, I want to quickly mention one of the uses of a stack. And so that's converting a recursive method into a non-recursive method. So to understand how this actually works is that you need to understand how methods or functions are typically implemented in many programming languages. Right. So here's a very, very simple recursive method. Well, this is a method that's implemented recursively. You would never implement it this way probably in practice. Right. So this method simply computes 10 raised to the power n. Right? If you were to implement this on your own, you would probably just write this with a loop, right? Write a loop, multiplies 10 n times, right? You could do it recursively as well. So the recursive implementation looks something like the following. This only works for positive, non-negative values of n, right? So at the top, we have our base case, right? So if n is 0, the result is just 1, right? 10 to the 0 is 1, and you're done, right? So at the end, we're going to return the 1 in this case, right? We'll return the result. If n is not 0, then all you're going to do is you're going to calculate 10 times the next smaller power of 1, right? So 10 squared is like 10 times 10 to the 1, right? 10 cubed is 10 times 10 squared, and so on and so on and so forth, right? And so there's your recursive call right there. All right, so what happens when you actually call this method in a language like Java? Right? Well, the following happens. Right? So I'm going to compute 10 to the power of 3. Right? So there's my variable x. It's going to hold the result. Right? Before we can hold the result, though, we have to actually run this method. And so that power of 10 method gets called. And the way this works in Java is that somewhere in memory, the method actually runs. Right? So more precisely, an instance of the method actually runs. Right? So power of 10 pops up somewhere in memory. If our method here has a parameter, n, so in the chunk of memory that power of 10 is running in, there's a little box called n that stores the value of the parameter. Right? And so we're calling power of 10 with the value 3. Right? Now what does power of 10 do if the value is 3? Well, it's not the base case, so it falls into the recursive case. Right? And the recursive case says compute 10 times power of 10, 2. Now, the way that recursive methods work is that that recursive call does not run in the same memory as this recursive call. Right? Instead, a new instance of the method appears in memory. Right? This time running with a value of n equal to 2. Right? So 2 is not a base case, so what happens? Well, there's a recursive call. Right? So it calls itself recursively, this time computing 10 to the power 1. Right? And again, this version of power of 10 does not run here. It does not run here. Right? It runs in a new instance of the method. Right? So now when n is 1, we're going to recursively call 10 to the power 0. Right? So a new instance of the method appears. Right? And now we're in a base case. Right? So if n is 0, we know the answer is 1. So the result we can now scribble in as 1. Right? And then we return the result. Right? So when you return the result, that 1 comes back up to here and replaces the power of 10, 0. So the 1 returns, right? So the result for the previous recursive call can now be computed, right? Now that this method is done, it can disappear, right? And our result here is 10. So we now have an answer for this result, so we can pass that answer back up to the previous version of power of 10, right? This one's now done, so it can disappear. We now have 100 here, so we can pass that value back to the previous power of 10. Right? This one's done, so it can go away. Right? That's now 1,000, so we now have an answer here, which we can return back to the caller over here. Right? And now this method is done, so it can go away. Right? So notice what's happening in that sequence of method calls. Right? So here was our first method call, right? And that ended up causing all of this to happen over here. Oh, there we go. Just give it a second to make sure it's not a false alarm. There you go. So that thing's still blinking, so I'm just going to wait a second. I don't know if it's it could be a test as well, so. That's going to be really annoying if that still keeps blinking all the time. Oh, there we go. Oh, no, never mind. All right, I'm going to continue. If the alarm comes on again, I guess we'll split. All right, so notice what happens here when you call a recursive method, right? Every recursive invocation of the method, right, requires more memory, right, for the next version of the method to run in. Right? And so if you try to solve a very large problem using recursion, right, it's possible that you end up using a lot of memory. Right? Every recursive call requires some memory to run in, and you can't return that memory back to the computer, or to the system, I suppose, until that version of the recursive method is done running. Right? So notice here, right, the first call can't finish running until we've made the last recursive call to the method, right? The recursive call that reaches the base case. And so when you try to solve very large problems using recursion, you can run out of memory. The reason you can run out of memory is because the space, or the memory that's used to store or to run the methods in, is that region of memory is much smaller than the region of memory that's available to your entire program. Right? So these are run in what's called the stack, the call stack. Right? And in most modern, in the C-like programming languages, the call stack has a limited size. And so you're limited in the size of the problems that you can solve using recursion. Right? Okay, so if you're trying to solve a large problem using recursion, or if you need to solve a large problem using recursion, one solution is to turn your recursive method into a non-recursive one. Right? The problem with recursion is that, or with many recursive methods, is that it's not always obvious how you turn the recursive solution into an iterative one. The basic idea, though, is to simulate what's going on in this call stack here. Right? So for a simple method like power of 10, it's pretty easy to do the simulation. In more complicated methods, it's a little bit harder to do. But I'm going to show you what you can do for the power of 10 method. Right? So the basic idea is that you want to emulate what the language is doing with the call stack, right? And you can do that by creating your own, by using your own stack implementation. Right? So the idea is you want to use your stack to store some information to remember what needs to be done whenever a recursive call returns. Right? So for example, in power of 10, right, every time a recursive call returns, something happens. Right? You take the value of the recursive call and you multiply it by something, right? You multiply it, oh, I shouldn't have done this, sorry. You multiply it by 10. Right? Okay, so we want to simulate what the virtual machine is doing during the recursive method, right? So when each recursive call returns, right, we want to remember that we need to multiply that result by 10. So we're going to create a little stack, and we're going to push a 10 onto the stack. Right? Now, during each recursive call, right, something happens to the value of n. Right? So every time we recursively call power of 10, the value of n goes down by 1 each time. Right? It turns out n is the size of our problem in this case, right? And you know that in recursion, you want the size of the problem to always decrease, right? So n goes down by 1, right? And so when you go to turn this into a recursive, so when you go to return power of 10, so when you go to turn power of 10 into an iterative method, we can do the following. Right? So we're going to make a stack of integers this time instead of a stack of strings. Right? We're going to try to compute 10 to the power n. So while n is greater than 0, right, we're just going to push a 10 onto that stack. Right? So that simulates remembering to have to multiply the recursive call by 10. Right? And then we're going to simulate recursively calling power of 10. So we're going to call power of 10 with a value of n that's 1 less than before. Right? And so what does this do? Well, this pushes n tens onto the stack. Right? All right, so remember every base case eventually, every recursive method eventually reaches its base case. Right? And so in this case, when we reach the base case, we know that the answer is 1. Right? So I can start now to accumulate our result from the base case. Right? So after we've done all this, we've hit our base case, and we know that the answer is 1. Right? And now we undo everything that we remembered from the stack. Right? So we're going to pop the stack until it's empty. Right? Remember, the values on the stack are the values that we have to multiply the result by. Right? And so we're just going to multiply the values that we pop off the stack into the result. So while the stack is not empty, right, we're going to take the result and multiply it by whatever's on the stack. So our stack just contains a bunch of 10s. Right? So this multiplies 10 n times, right? And now you return the result. Right? And so there's how you can use the stack, to emulate what's actually happening when you are in the recursive method. Right? So that probably seems overcomplicated to most of you, right? You could just write a little for loop that multiplies 10 n times, right? But it illustrates the basic idea of using a stack to convert a recursive method into an iterative one. That's a lie. There is not another example here. Sorry, I forgot to edit this slide. In your data structures course, you might, depending on, you're definitely going to encounter recursive methods. When you write methods on graphs and trees, they are often easiest to express recursively. Right? You might learn or be asked to convert them into iterative versions. Right? Many of the tree and graph methods, when you convert them to iterative methods, use either a stack or something called a queue to help you do the work. Right. Okay, so there's a little aside. I'm now going to go back to trying to implement one of these stacks. So I showed you how to implement a stack with a list, right? And you can use the ideas there to figure out how to implement the stack using an array instead. Right? So remember, a list holds a variable number of elements, right? But in an array always holds a fixed number of elements, right? And so with the list, if you want to add new elements to the list, you just call add, right? And the list takes care of figuring out how to add stuff to the end of the list. Right? Here we've got a fixed number of elements in our array, so we have to now manage what happens when you add something to the end of the array and there's no more space left in the array. Similarly, when we're removing stuff from the array, we're going to have to figure out how to, when you're popping elements off the stack, right, you want to remove something from the end of the array now. So end in quotes, because it's not actually the last element in the array, right? It's whatever element is at the top of the stack. And so you can't reduce the size of the array either, right? So arrays have a fixed size in Java. So if you want to increase the size of the array, or if you want to decrease the size of the array, the only way you can do this is to make a new array. Right? If you want a bigger array, you make a new bigger array, copy all the elements into the new bigger array. Right? If you want to reduce the size of the array, you make a new smaller array, and copy whatever elements you want to keep into the smaller array. All right, so if we have a fixed size array, and you want to simulate adding stuff or pushing elements and popping elements off the top of the stack, right? It doesn't make sense to keep on resizing the array each time, right? Instead, you want to make an array of some size, right? You want to, if you pop something into the array, you just want to add it to the array if there's room in the array, right? And if you want to remove something from the array, you just want to remove something from the array, right? You don't want to keep on changing its size if you don't have to. And so we need to remember where in the array is the actual top of the stack. Right? And so here's our stack, and this time we're going to make a stack of ints. Right? So if you're going to use an array to implement this thing, you need a field that is an array. Right? So the ARR is our field that's going to store the integers of our stack. Right? And we're going to record where in this array is the top element of the stack. Right? If the stack is empty, we're going to set top index to -1. Right? So top index is simply what is the index of the top element of the stack. Okay, so to make an empty stack, what do? Right? Well, you make a new array. So remember, constructor has to initialize the fields of the class. So we're going to make an array of some size. It looks like we're going to make an array of size 16 in this case. Right? And we're going to set top index to -1. Right? So there's our new array. Right? Now remember, in Java, you actually do have an array of 16 integers here. Right? You have this array here has 16 zeros in it. Right? Our stack is empty though. Right? So that's the thing you have to remember. Right? So even though the array has 16 values in it, the stack has no values in it. And so we're going to record that piece of information by setting top index to -1. Right? And so when you make a new empty stack, what you end up with is an array of all zeros, right? And the top index equal to -1. Right? So that represents our empty stack. Oops, sorry. Okay, so when you push a value onto the stack, we want to add the value to the quote-unquote end of the array. Right? So the end of the array in this case is going to be at index 0. Right? So top index you can think of as marking the end of the array. Right? So the pushing a value onto the stack, we add 1 to top index. Right? Because remember, top index is the index of the element that's currently at the back of the array. Right? So we're going to add 1 to that to move to the next element, the next free element in the array. Right? And then we're just going to set that element to whatever value is pushed onto the stack. Right? So if I push a 7 onto the stack, right, we're going to add 1 to top index, so top index becomes 0. Right? And then I'm going to fill in the element at that index with the number 7, right, whatever was pushed onto the stack. Right? If you push a -5 onto the stack, right, top index goes up by 1. Right? So it becomes 1, and then we're going to fill in that element with the value that was pushed onto the stack. So it becomes -5. Right? Whoops. Right? And so on and so on and so on. Right? To pop a value from the stack, right, you want to remove the last element in the array. Well, the last element that's on the stack that's in the array. Right? Well, I know where that element is, right? That's what top index is for. Right? Top index records the location of the top element of the stack. Right? So I can simply go and look at that element, right? Remember what it is. Right? Then I'm going to decrease top index by 1 to simulate removing the element from the stack. Right? And return the value that remembered up in this step up here. Right? So like this. Right? So we have a 7 and a 5 on the stack, and then if I pop the stack, right, I'm going to look at whatever was top index, so top index was 1. Right? I'm going to remember its value is -5. Right? I'm going to decrease top index by 1, so our new top element is the 7. Right? And I'm going to return whatever value I remembered in the previous step. So I'm going to return the -5 in this case. Right? You don't have to go into the array and turn that into a 0. Right? The fact that there are zeros here is insignificant. Right? Because you can push zeros onto the stack as well if you wanted to. Right? So all that matters here is keeping track of the top index. Right? The actual values in the array, we don't care about at this point in time. Right? Okay, so what does pop look like? So ignore the if statement at the beginning. Right? So to pop an element from the top of the stack, we want to remember what is the element currently at the top of the stack. That element is at top index, right? And it's in an array, so I can just use array indexing to get that element. Right? I want to adjust the top index, so I want to decrease it by 1 to simulate removing the element from the stack, right? Or moving the top pointer down 1 element in the stack. Right? So remove 1 from top index and then return the element that we remembered in the previous step. Right? Don't forget that you can't pop an empty stack. Right? So how do I know if the stack is empty? Right? Our stack is empty when top index is -1. Right? So if the stack is empty, we're going to throw an exception. In this case, we throw something called an empty stack exception. Right? All right, so what about push? So pop is relatively straightforward, right? Grab the current element at the top of the stack, right? Remember what it is, right? Decrease our top index by 1 to simulate removing the element from the stack, right? And then return the element. Right? Notice that all of these operations here, these are all constant time operations, right? So to access an element in an array using an index, that's a constant time operation, so that's O1. Right? Subtracting 1 from an integer is a constant time operation, so that's also in O1. And returning a value also runs in O1 time. Right? So these set of operations here are all constant time, so the worst case complexity of pop is O1. Okay, now what about push? So push is a little bit more complicated. And so here, we've pushed 15 elements onto the stack. Right? So top index is currently 14. Right? I can safely push one more element onto the stack because I've got one free space at the end of the array. If I try to push another element onto the stack, I can't do it safely because there's no room to store that element in this array. Right? So for push, right, as long as the top index is less than the length of the array minus 1, right, so here our array length is 16, right? If top index is 14, that's the last time I can safely push something onto the stack, right? So is 14 less than 16 minus 1? The answer is yes, right? Then to push the element onto the stack, it's straightforward, right? We add 1 to the top index and then set the element of the array at top index to the element that was pushed onto the stack, right? If this condition is not true, so in other words, if this value is filled in and top index is 15, right, that's when we fall into the else part here. Right. Okay, so if we run out of capacity in the current array, right, what we need to do is we need to increase the capacity of the current array. Right? And so there is no way to do that in Java, right? So you cannot take an existing array and suddenly make it larger. Right? The best that you can do is to make a new array. Right? So you want to make a new array that's larger than the current array. Right? Exactly how much larger, we'll see in just a second. Right? When you make the new array, right, you have to remember there's elements already in the stack. So you want to take all the old elements, or all the current elements that are in the stack, and copy those into the new array. Right? So copy the old array into the new array. Right? Now we've made a new array, and our stack has a reference to that array. Right? It's this ARR. So we have to make this ARR now point at or refer to the new array. Right? So now you've got room in the new array. Now you've got room in the array to hold a new element. So finally, I can push the element onto the stack. Right? So what does that look like? Right? So make a new array with greater capacity. So we'll make a new array. Right? How big should we make the array? Well, it has to be at least the current array length plus 1. Right? It turns out you don't want to do plus 1. Right? Instead, I'm going to multiply it by 2. So I'm going to double the current capacity of the array. Right? So starting with an array of 16, it's going to become 32. Right? If that array becomes full, it's going to become 64. And if that array becomes full, it's going to become 128, and so on and so on and so forth. Right? So I'm going to choose to double the previous capacity. I'll come back to this point in just a moment. So I've now got a new array, but it's got a bunch of zeros in it. I need to copy the original array into the new array. Right? So you write a little loop, right, that runs over the old array, right, or the current array. Right? So for this loop runs as long as I is less than the current array length. Right? And you're just going to copy whatever's in the current array into new array. Right? Now don't forget, our stack is keeping track of its own array, right? So you have to make this array now point at or refer to new array. Right? And now finally, I can push the element onto the stack. Right? I'm going to do this recursively. So I'm just going to call push again, pushing the element onto the stack. When you call it recursively, right, this condition is no longer true now. Right? Your new array is now bigger, so top index is now less than the new array length minus 1. So now this stuff happens here, right? And the recursive call stops. Okay, so this step right here. Oh, ask any questions about what just happened here, right? Make a new array, copy the old array into the new array, and then push the element onto the top of the stack. All right, so back here. Why did I multiply by 2, right? So it turns out if you add 1 to the new array, right? If you make a new array that's 1 bigger than the previous array, the program will work, right? So your stack will work, right? So what happens, right? So I have an array of size 16, right? I push a new element on, I have a stack with 16 elements on it, right? I push a new element onto the stack, right? And now I make this an array of size 17, right? So to make this an array of size 17, I have to copy the 16 elements that are currently in the array into the new array. And then push the element onto the top of the array. Right? Now I push another element on top of the stack. Right? So now I make a new array of size 18. Right? Copy the 17 elements that are currently in the stack to the new array. Right? Then push the element on top of the stack. Right? And then you push another element onto the stack. So now I make a new array, right? And see what happens here is that every time you try to push one more element onto the stack, right, you perform an operation that has to do something to all the elements in the current stack, right? So if you increase the capacity by 1 in each step, push becomes worst case O(n) squared, which you don't want. Sorry, on average it becomes O(n) squared, O(n), which is what you don't want, right? Every time you add a new element to the stack, right, you have to perform n operations to copy the current n elements into the new array. It turns out if you double the size of the array, or if you if you make a new array that is some multiple bigger than the current array, right? So any value that's bigger than 1 here works, right? So 1.5 works, 1.25 works, right? Any value greater than 1, right? If you do that and you analyze the problem, or you analyze the resulting complexity, it turns out it's always, on average, you end up with O(1) complexity, right? Every once in a while when you have to resize the array, right, it's O(n), right? But if you consider when does this operation actually have to happen, and you average out, and you compute the average complexity, it becomes O(1). Right? And so you want to multiply you want to increase the size of the current array by multiplying, by making a new array that is some multiple bigger than the current array. Okay, so this process here, where you make a new array, copy the elements into the new array, it turns out that's fairly common if you're going to work with arrays, right? So it's a common operation that you want to create a new, larger array when you run out of capacity in the existing array, right? Similarly, you might have an array where you don't need the elements at the end anymore, so you want to reduce the capacity of the array, right? And so this process of copying an array into a larger or smaller new array is common enough that the Java language designers made a method for you that does this, right? So the method is called arrays copy of, which we've seen before. But we can now use it to make a new array that is a copy of an existing array, this time having greater capacity, right? So instead of writing all of this, right, you can just write that, which is nice, right? So the method copy of makes a copy of that array by creating a new array of that length or that capacity, right? And copying the elements from that array into the new array, right? So instead of making the array yourself and writing the loop to copy the elements into the new array, right, you can just use copy of, and that takes care of everything for you, right? And there is your implementation of a stack using an array. Oops, sorry. Right. Any questions about that implementation? All right. I guess we'll stop things there. So in the next lecture, I guess tomorrow, we'll implement a stack a third way, this time using a linked sequence of nodes. And that's going to introduce a new concept for many of you, I guess, if you haven't seen a linked sequence before. All right. So we're done for today. I'll see you again tomorrow morning.